Hello everyone, welcome back. In this video, we're going to start the next chapter, which is on integral calculus. Now back in chapter 2, when we first started studying calculus, we introduced the tangent line problem, and this led us to define the derivative, which is the central idea in differential calculus. So in a very similar way, we will look at introducing the area problem, and it will be used to define the definite integral. And this will be the central idea for integral calculus. Now, an important result, which we will learn later, will be called the fundamental theorem of calculus, and it will connect the two branches of calculus. So let's first start off with the area problem. So let's consider a function y equals f of x, and suppose that we're interested in finding the area that falls between the curve and the x-axis on an interval from a to b. So now the question is, how do we determine the area of this region? Well, the way that we will calculate the area underneath the curve will be very analogous to how we determined the slope of the tangent line. So if you recall from the tangent line problem, what we did first was approximate the slope of the tangent lines by using secant lines. We can then calculate the exact slope of the tangent line by taking limits. So we will apply the same approach to the area problem. So let's first approximate the area underneath the curve. So one approach to approximating the area underneath the curve is by using rectangles. So what we'll do is first subdivide the interval from a to b into equal subintervals that have a length of delta x. We can then use rectangles within each of those intervals to approximate the area. So on the right, the example shows an approximation using 4 rectangles. So we first subdivide the interval from a to b into smaller subintervals, and the endpoints of these intervals are given by the x-coordinates x1, x2, x3, and x4. And each of these subintervals have a length of delta x. Now the heights of each of these 4 rectangles are given by the function values at each of these x-coordinates. So in the first rectangle, the height is given by f of x1. The second rectangle has a height of f of x2. The third is f of x3, and the fourth is f of x4. We can then calculate the areas of these rectangles by taking the function values of these x-coordinates and then multiplying it by the width of the rectangles, which are all given by delta x. Now in general, we can approximate the area by first subdividing the intervals into n smaller subintervals, and then using rectangles with width delta x and heights f of xi, where I goes from 1 to n. So in general, we can approximate the area by using n rectangles by first subdividing the interval into n smaller subintervals, and then using rectangles with width delta x and height f of xi, where I goes from 1 to n. Now we give a special name to this approximation. This is called a Riemann sum and is given by this formula. So R of n, which is the sum from I equals 1 to n of f of xi times delta x. And the summation notation is just a shorthand for this sum calculation. We take the heights of each rectangles, which are f of x1, f of x2, and so on up to f of xn, and then we multiply it by the width of each rectangle, which are all delta x. Now the way that we calculate the width, or delta x, is by using this formula. We take b minus a divided by n. So a and b are the endpoints of our interval, and n is the number of subintervals or the number of rectangles. Now x of I is given by this formula. So this is how we calculate the endpoints of the subintervals, and is given by a plus I times delta x. So let's have a look at an example of using a Riemann sum to approximate the area underneath the curve. So let's approximate the area underneath the curve y equals x squared on the interval from 0 to 4 using Riemann sums R2 and R4. So in other words, we're going to approximate the area by using 2 rectangles and then 4 rectangles. So R2 is given by the sum from 1 to 2 of f of xi times delta x. So what we need to do is calculate the width of the rectangle, delta x, as well as the x coordinates, xi. So if you were to write out the sum, this is given by f of x1 times delta x plus f of x2 times delta x. So let's first calculate delta x, which is the width of each rectangle, which is given by b minus a divided by n. And our interval we're working with is from 0 to 4. So what we want to use is 2 rectangles. And so delta x will be given by 4 minus 0 divided by 2. And so this tells us that the width of each rectangle has a length of 2. Next, we can calculate the x-coordinates of each of the endpoints. So that's given by a plus I times delta x. So we know that a is equal to 0. And we just calculated delta x to be 2. And so this tells us that x of I is given by the formula 2i. So in our Riemann sum, what we want to look for is x1 and x2. So to find x1, our index I is equal to 1. So x1 will be 2 times 1, which is equal to 2. And so that tells us that x1 has an x-coordinate of 2. Now x2 is given by 2 times 2, which is 4. And so x2 has an x-coordinate of 4. So let's have a look at drawing the approximating rectangles. So here is the function y equals x squared. And we have the x-coordinates at 2 and at 4. And so the height of each of these rectangles is given by the function values at these x-coordinates. So the first rectangle will have a height of f of x1, which is f of 2. And the height of the second rectangle is given by the function value at the second x-coordinate, which is 4. So f of 4 is the height of the second rectangle. So now we can calculate the approximation of the area. So R2 is f of x1 times delta x plus f of x2 times delta x. So we know that f of x, or x1 is equal to 2. delta x is also 2, and f of x2 is f of 4, and delta x is 2. And so the Riemann sum is f of 2, so we substitute 2 into our function, and our function is x squared. So that gives us 2 squared times 2 plus 4 squared times 2. So this gives us 8 plus 32, or 40. And since we're looking at the area of the rectangles, this will have units of 40 squared units. So now let's also use 4 rectangles to approximate the area. So our 4 is given by the sum from I equals 1 to 4 of xi times delta x. And if you were to write out the sum, this would be f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x plus f of x4 times delta x. So let's first determine the width of each of these rectangles. So delta x is b minus a over n. So here we're using 4 rectangles, so n is 4. So delta x is 4 minus 0 over 4, which is 1. And then let's also determine the formula for the x-coordinates. So xi is given by a plus I times delta x. So a is 0, and we know that delta x was equal to 1. And so this tells us that xi is given by I. And in our Riemann sum, what we need is x1, x2, x3, and x4. So x1 is equal to 1, x2 is equal to 2, x3 is 3, and x4 is 4. So let's draw the approximating rectangles. So we have coordinates 1, 2, 3, and 4. So we'll have 4 rectangles. And each of these heights of these rectangles will be f of 4, f of 3, f of 2, and f of 1. So our 4 is given by f of 1 times delta x plus f of 2 times delta x plus f of 3 times delta x plus f of 4 times delta x. So we know that the width of each rectangle is 1. So this is 1 squared times 1 plus 2 squared times 1 plus 3 squared times 1 plus 4 squared times 1. So this is 1 plus 4 plus 9 plus 16 which gives us 30 units squared. And so the approximation using 2 rectangles gave us 40 squared units, and the approximation using 4 rectangles gave us 30 square units. So how can we determine a better approximation to the area underneath the curve? Well, we could keep using more and more rectangles, and that will give us a better approximation. And to find the exact area underneath the curve, we can let the number of rectangles go to infinity. So in other words, we want to let the limit of n going to infinity, and that will give us the exact area underneath the curve. So we make the following definition. The area A of the region that lies under the graph of the continuous function f is the limit of the sum of the areas of approximating rectangles. And so A is the limit of the Riemann sum Rn as n goes to infinity. And we'll look at some examples of calculating the exact areas in the next video.